Welcome to this video on multinomial choice. Multinomial choice is choice between alternatives that cannot be ordered in the sense that the ordering is not the same for each decision maker. And multinomial choice models are closely related to utility maximization, and this is actually what this paper by McFadden that I've put here on the slide established. So McFadden looked at models that were used in other disciplines and developed a foundation that is related to utility maximization. And this is what we're going to discuss here, and of course also how these models work more generally. Okay. So what we'll have is capital J alternatives. As I said, they cannot be ordered in the sense that the ordering in terms of utilities will in general be different across decision makers. And examples include the case that McFadden studied. So McFadden studied the choice between different modes of traveling, commuting to work. So he studied the choice between traveling by bus and traveling by car. And because he had a utility foundation and he expressed utilities in terms of characteristics of these alternatives, he could infer from the data what the preference of people was for travel time versus travel cost. And then, and this was the big contribution, he used that knowledge and the structure of the model to predict what demand would be for a completely different new alternative travel mode. And this was back then the BART commuter train. That was a commuter train in the Bay Area. The Bay Area is the area around San Francisco. And he was back then in Berkeley, so he studied actually a local problem, but became famous and later on even got the Nobel Prize for all this. Now, other examples are choice between different types of health insurance. So also these are different in multiple dimensions, coverage, deductibles, or choice of a brand of a soft drink. So multinomial choice models are very important in marketing when consumer data are analyzed. So brand of a soft drink between Coca-Cola, Pepsi, and no-name cola, for instance. What we want to do here is to relate choice probabilities or choices to two types of variables that we can measure. So one type would be alternative varying regressors. An example would be income minus price. So these are characteristics of alternative J if chosen by individual I. Income minus price, so that would be the money that is left for other consumption, let's say. And the second type of measurable variable would be alternative invariant regressors, WI. So these are characteristics of the decision situation or the decision maker. So here think of the distinction between old and young people. So clearly, it doesn't change whether you're old or young when you choose a particular alternative, but older people might have different preferences across alternatives than younger people, and we want to learn about that from data. Now let's look in more detail at the random utility foundation. So as I said, this is due to McFadden largely. I's utility when choosing alternative J is specified as depending on characteristics. So Zij with coefficient alpha and Wi with coefficient gamma j. And then there is a so-called taste shock that is epsilon ij. Okay, so this xij beta is just another way of writing the sum of these two elements here. And xij beta is sometimes also referred to as the average utility. And one can generalize this to be nonlinear in x, ij, or in these variables, but normally this is actually not done in practice. Then there's this taste shock epsilon ij. So what you see here is that we actually have one taste shock for each alternative. The usual assumption is that the coefficient on the z's, which is this alpha here, is the same across alternatives. So an example makes that clear what that means. An example would be that the utility of traveling by bus depends in the same way on travel time as the utility of traveling by car. Okay, so that's clearly restrictive, but it's often deemed reasonable as an assumption. Otherwise, the model becomes actually too flexible. So for that reason, it's sometimes argued to be desirable to impose such restrictions. Now, one more word about this business here, Zij alpha plus Wi gamma j. So what you have here is alternative varying coefficients or parameters, these gamma j's. What you can do is you can create lots of interaction terms between Wi and alternative indicators, and then each interaction term would have its own coefficient gamma j, but then what you actually have is a parameter vector that is not alternative specific, and the regressors which are, so the xij would include the zij and all the interactions between wi and the alternative indicators. And this just helps us in the sense that we can thereby use a more compact notation. Utility maximization now means that the utility maximizing individual I will choose alternative j if the utility from choosing alternative j is no less than the utility from all alternatives j prime. And usually we're going to assume that epsilon ij, these epsilon ij's are continuously distributed, so ties will happen with probability 0, and here we can largely ignore them, in particular when we derive choice probabilities. But you want to be, of course, consistent with your notation. So formally it could be that this holds, so that's an if, that's not an if and only if, that's what I mean to say. Good, so the object of interest is beta and marginal effects. Marginal effects would be changes in the probabilities to choose certain alternatives, and this is again related to price elasticities. So price elasticities are the percentage changes in demand when price changes by 1%. Now, this is a very general framework. So far I haven't stated any assumption on the distributions of those epsilon ij's. We're going to get there, and in some sense this slide here is motivation for that. The one thing I have imposed is a functional form for the utility that is additive in characteristics and taste shocks. Now, let's think about the implied choice probabilities. So the probability to choose, for instance, alternative number 1 will actually depend on all the xij's and all the epsilons. Why is that? Well, I'm doing utility comparisons, and if another alternative's xij changes, or if another alternative's epsilon ij changes, it might impact the decision whether or not to purchase option number 1, or to choose j is equal to 1. So formally we have that the probability that alternative 1 is chosen given the characteristics of all the alternatives is the probability that the utility for alternative number 1 is bigger than the utility for alternative number 2, and at the same time the utility for alternative 1 is bigger than the utility for alternative 3, up to alternative j. So also the utility for alternative number 1 is bigger than the utility for alternative j. And this is a joint event here. So you see the commas here. Now, in the next line, all I've done is to plug in the functional form of the utility function, and I've brought always the epsilon that is not the epsilon associated with the first alternative. I've brought that on the right hand side of an inequality. Okay, so I can write this joint event here like this. Okay, so the first condition is that the first random utility is bigger than the second random utility. So when you write that out and you bring the epsilon I2 to the left hand side, then what you will get is that epsilon I2 is less than or equal than the difference in the x's, x1 minus x2, xi1 minus xi2 times beta plus epsilon I1. And I can do the exact same thing for the other alternatives. So I'm getting here j minus 1 statements. Notice that this is also here about j minus 1 statements. So I get one for utility 2, one for utility 3, up to utility j, and it's always involving utility 1. So it's capital J minus 1 inequalities, and I still have capital J minus 1 inequalities. So these capital J minus 1 inequalities, this is again the probability for a joint event. I can write this as a j minus 1 dimensional integral. Okay, so forget about this first one here. Just look at the second up to this one here. So these are j minus 1. There's a j minus 1 dimensional integral. And what am I integrating over? I'm integrating over the distribution of the joint distribution of all the epsilons evaluated at these values. So over all the epsilons. Here, this is integrating over epsilon 2, 3, up to epsilon j minus 1. And then the very first one is integrating over epsilon I1. So this is always integrating over these epsilons that are here on the right hand side of this inequality. But let's first look at the capital J minus 1 integral, the capital J minus 1 dimensional integral here. Here I'm always going from minus infinity up to, and here this quantity here is exactly what I had here. Okay, so xi1 minus xi2 beta plus epsilon I1. So epsilon I2 has to be less than or equal than that. So I'm going from minus infinity for epsilon I2 up to that value. This is just representing this inequality. This integral here is representing the second inequality, and so on. So in this last one here is representing this last inequality for a given epsilon I1, and then I still need to integrate out the epsilon I1, which is done here in this outermost integral. Now, this is basically true by definition here, right? I'm just writing out what it means to get a choice probability when there is a utility maximization and when exactly one alternative is picked. What you can see from this here is that, yeah, it's going to be challenging to estimate a very, very general version of this model, simply because I'm going to have to evaluate a j-dimensional integral, which is doable, but not so fast. Okay, so there's some benefits to speeding this up when one can use functional form assumptions in a clever way, and this is exactly what is being done now. So I'm making a big jump here, and the big jump is that I'm just giving you here the expression for the multinomial logit choice probabilities. Okay, so this expression is extremely simple. Okay, so on the previous slide we have seen a multidimensional integral look kind of messy, and when one makes the right assumptions on the right assumption on the epsilon ij's distributional assumption, then one gets this choice probability here. How does this look like? Again, this is the exact same thing we had on the previous slide. Well, for alternative j, so the probability that alternative j is chosen, given the characteristics of all the alternatives, is going to be the exponential function of xij beta divided by the sum over all alternatives j prime in the choice set, including j, of the exponential function xij beta. And this is actually very similar to what we have seen for the binary logit model. Now, I say binary logit model, so this should ring a bell. So indeed, what is the case here is that the assumption that we will have to make on the distribution of the epsilon ij's is that they're type 1 extreme value. Okay, so when the epsilon ij's are type 1 extreme value, then we're going to get this very simple expression for the choice probability for alternative j. And you can see, by the way, directly that these choice probabilities will sum up to 1 across alternatives, because then the numerator will sum up to what is the denominator, so that will play out nicely. So here it's written out in terms of xij beta for the specification of the utility function or the mean utility. We can also write it down in terms of zij's and wi, but then it's of course still the same type of expression that we get. Now, let's look at this second formulation and think about normalizations. What I can do is I can divide both the numerator and the denominator of this expression here by the exponential function evaluated at zi1 alpha plus wi gamma 1. So that would be the exponential function evaluated at the mean utility for alternative number 1. I can do this. I divide the numerator by this and the denominator, which means I will divide all the terms in this sum of the denominator by it. Now this is the exponential function evaluated at something divided by the exponential function evaluated at something. So I'm going to have the exponential function evaluated at the difference between these two arguments. Here, this gives an expression like this. What is this? This is the mean utility of alternative j minus the mean utility of alternative 1. So I'm getting the difference in the z's, and here I'm getting the difference in the coefficients gamma. And this is very natural. So when you think of it in terms of utility comparisons, all that matters is the ordering of alternatives in terms of utilities. So when I'm saying I'm looking at the utilities relative to the utility of the first alternative, it will preserve the ordering. Okay, so it's basically taking out utility levels. So we're we're heading here towards talking about a location normalization. So here what we've done is actually by doing this operation, we've taken the first alternative as our base alternative. Normalizations just mean, as before, that we need to impose something because otherwise the model is too flexible, but whatever we impose is fine because it will not restrict the model's prediction in terms of the implied choice probabilities. Or put differently, we can only identify the difference in those gammas relative to one of the gammas. We need to fix one of them, and that's, as I said, location normalization. And also we cannot identify the coefficient on a constant term in Zij. Why? Because I'm going to always have here the difference in the Zij's, right? So if the first element is a 1, then this will always go away. So I can never, so it's 1 minus 1 for that first element, so the alpha will never be identified. And usually what one does is one imposes the normalization that one coefficient, for instance, gamma 1 is equal to 0 and no constant term is included in Zij. Marginal effects. So as before, marginal effects are changes in choice probabilities when either a Zij changes, or when a Zik changes, or when Wi changes. And here I will study all of these three, in turn. Good. So let's just in terms of notation say that the probability that alternative J is chosen by I given all the x's, or if you like, given all the z's and the w, is denoted by Pij. Now I'm going to look at the change in Pij when I change Zij. So the change in the probability that I choose is alternative J when characteristics of that one alternative do change. So what do I have to do? And this actually is very similar to what we have seen for the binary logit model. It's not a surprise because this is, in the end of the day, a generalization of the binary logit model, as you can simply see by looking at the functional form. So let's take that derivative back when we studied the binary logit model. We had to use the quotient rule for taking that derivative, and we have to do that now as well because Zij enters the numerator here, and it also enters the denominator when J prime is equal to J, because it's a sum over all these expressions, and one of them is going to be for J prime is equal to J. So what we'll get is the outer derivative of the numerator times the inner derivative. That would be the derivative of this expression here with respect to Zij, so that's just alpha times the denominator. And I've split this now up into two parts. So here we have the denominator squared already, and then I have minus the numerator times the derivative of the denominator with respect to Zij. So that's just the outer derivative here. That's the exponential function evaluated at Zij. So here J prime is equal to J alpha plus Wi gamma J. And then again the inner derivative. So that's going to be when J prime is equal to J, the derivative of Zij alpha plus Wi gamma J with respect to Zij. So that's again just alpha, and here I have the denominator squared again. Now, once one looks at this, we can do something that parallels what we have done for the binary logit model, which is to write this in terms of choice probabilities. You see here that the denominator is the original denominator is squared. So one of these terms actually cancels with this term here. This is the exact same term as here. So the square goes away. This term here goes away. So what stays is this times alpha times this and then not squared. Okay, and this is just, if you compare it to this expression here, Pij times then the alpha that comes from here. So here's the alpha. So that's the first. And the second is minus. And what we do have here is this expression appears twice. Okay, so I'm getting Pij squared. And again, times alpha. So I can write this as P times 1 minus P times alpha. So this makes the parallel to the binary logit model very salient, because also there we had Pij times 1 minus Pij times alpha. With the one difference that we can now write this down for each j. And in the binary logit model, we just had a P. Good. So next, let's look at the derivative of the choice probability with respect to characteristics of other alternatives. So that's a very similar and actually simpler derivation than what we've just seen. So again, this is the starting point. This is my Pij. So what I will now have to do is to take the derivative with respect to Zik. And in fact, Zik does not enter the numerator. So when I just use the formula for the quotient rule, the first of these two terms goes away anyway. So what I will then have is the numerator, which is minus the numerator times the derivative of the denominator with respect to Zik. So Zik is only appearing when j prime is equal to k, and then I get Zik alpha plus wi gamma k as an argument of the exponential function. So that's exactly here the outer derivative. It's this one element of that sum times the inner derivative, which is again alpha, because then I'm going to have Zik alpha, and then I take the derivative with respect to Zik, so I'm ending up with alpha. And what you see here in the denominator of this derivative is just the original denominator squared. Okay, and then when you look at this, then you will see that here I have this numerator, here I have that numerator, and here I have the denominator squared. So I can write this as minus the probability that j is chosen times the probability that k is chosen times alpha, which is exactly this thing here. And third, we can take the derivative with respect to wi. So again, this is our starting point, Pij. And now the derivative with respect to wi works a little bit differently. What you get now is that wi actually enters each of the elements in the denominator. Okay, so before we had that one Zij or Zik only entered once in the denominator. Now it enters each element of the denominator. So things will look a little bit differently. So let's just go through this slowly and then just systematically using, again, the quotient rule. So this is the derivative of the numerator with respect to wi. So I'm going to get this expression here as the outer derivative times gamma j. This is exactly this expression here times the denominator. That's exactly this expression here, divided by the denominator squared minus, and this is just the numerator. And now it's getting interesting, because this is the derivative of the denominator with respect to wi. So what you have is that it's a sum of the exponential function evaluated at these arguments, and all you have to do is actually to realize that I'm taking the derivative of a sum, so it's the sum of the derivatives. So I'm getting here the sum, and now I'm indexing with j double prime just to make this distinction between the other sums more clear. This is the sum, and then I'm getting the outer derivative is always simply this expression here. So this term here is exactly this one here. The one difference is that I'm now writing j prime prime, and here also j double prime instead of the j prime, and then it's always times the inner derivative, and that is the gamma j double prime, and then again divided by the denominator squared. Now, what's cool is not this expression that we have already, like this one here. What's cool is the interpretation we can give to this. But for this, we need to first rewrite this again. So first, again, as before, one of the square terms cancels with this term here. So I'm getting Pij times gamma j as before. Okay, so the first one stays. Is very similar to what we found before. For the second one, I have here again this expression twice, so the product or the square of it. So I'm getting once Pij, because this is the numerator, and then I'm getting a sum, and that sum always has the inner derivative, so that's the gamma double prime, and times, and I can just pull this one expression that is left here into that sum, and then I'm able to write this actually as Pij double prime gamma j double prime. So what I'm getting is, when I collect terms, I see Pij here and here, I can write this as Pij times gamma j minus this term here. Okay? And this term here is actually the average gamma j across all alternatives. Not only the average, it's the weighted average, and it's weighted by the choice probabilities. So we can interpret what we get in terms of this logic. So to summarize, what we'll have is the marginal effects associated with changes in alternative varying characteristics zik or zij. So either when j is equal to k, so when its own characteristics, then it's going to be p times 1 minus p times alpha, and otherwise it's going to be minus Pij pik times alpha. So when you write this one out, it only has the second expression, and then j is the second element of that sum, and j is not equal to k anymore. And for changes in characteristics of the decision situation or the decision maker or alternative invariant characteristics, what we get is that the marginal effect is equal to Pij times the difference between the gamma j and the weighted average gamma j across alternatives, and weighted by the choice probabilities. Now, this is of course all for marginal changes in characteristics. What you can always do is you can also calculate simply changes in choice probabilities for discrete changes in characteristics when these characteristics are discrete. I'm not doing this here explicitly, but it's straightforward to do that. Notice that all these three marginal effects are actually proportional to the choice probability. Okay, so when a particular alternative j has a high p, then its marginal effect will also be bigger. Moreover, notice that the sign of the effect of own characteristics is the same as the sign of the coefficient. So if we find a particular sign for the coefficient. We already know what the sign of the own marginal effect is. Actually, we also know what the sign of the cross-marginal effect is, the marginal effect on the choice probabilities for other alternatives. It's the opposite sign, okay? And that is a little bit, like for the first and the last alternative in the order choice model, or that property here is like the property for the marginal effect in the binary choice model. This all is not true for the sign of the effect of changes in alternative invariant characteristics, so Wi. Here we have a parallel to the ordered choice model that it could be positive or negative depending on which alternative one looks at. What it really depends on is whether the gamma j is relatively big relative to the weighted average gamma j. Good. Now this brings us to welfare analysis. And welfare analysis is one of the really cool things one can do with this model. We have here a utility foundation, and we have a nice structure, and we have a very, very useful distributional assumptions that we can make, namely that the epsilons are type 1 extreme value. And this actually allows us to do welfare analysis, which I personally find pretty cool. And to me, this is the selling point of this model, next to being able to actually predict demand for alternatives that have never been there. Let's think about this step by step. So first of all, welfare effects are closely related to expected maximal utility. And we can think about expected maximal utility in that framework. So they can arise from either introducing new alternatives, or killing alternatives, or changing characteristics of existing alternatives. And think of changing characteristics as like the price is changing, right? Or there's innovation and they become better, the quality improves. Introducing new alternatives brings us back to McFadden's original application, where a new commuter train was introduced. And it's actually quite complex to think about this. So you can think of one consumer who would be completely oblivious to this, right? He would just prefer his car, would never ever choose the commuter train. So the welfare effect for this consumer would actually be zero, right? To first order. So of course, when there's less traffic, then he benefits too. But otherwise, if the characteristics of the alternative he chooses anyway will not be affected, then this consumer will not be affected in terms of welfare. Whereas other consumers who would actually choose that commuter train, they might be affected by quite a bit. And to think this through in terms of a model is very, very useful. So it's very complex, and we can use the model here to quantify welfare effects really in terms of money, in fact. Now, what are we going to look at? We're going to look at the change in income that is needed to make I as well off with the new alternative or the changed characteristics as compared to before. And this amount you have seen in microeconomics, that's called the compensating variation. And it's measured in terms of money. And here we have some randomness. So what we're going to do is we're going to look at the average or expected compensating variation across individuals. Or you can think of it as the compensating variation from an ex-ante perspective, veil of ignorance, and so on, before consumers learn about their epsilons. So that would be this expectation here. Okay, so this expectation is over the epsilons. So in order to study this, I have to switch gears, but this slide looks very complicated, but it only looks complicated because I've put in all the little steps that we need to take, and I found this derivation here always very useful, so therefore I want to share it with you. We have, formally speaking, these random utilities. Okay, why are there random utilities? Because there's a random quantity epsilon ij here, right? So the random utility consists of the average utility and the epsilon ij. Okay, and I'm assuming now that the epsilon ij is type 1 extreme value. Little aside, it's actually slightly wrong to call this here the average utility or the mean utility, because the mean of the epsilon ij, as we have seen before, is actually not 0, right? So the mean of epsilon ij is the mean of a type 1 extreme value distribution, and that is equal to Euler's constant, which was 0.57 and so on. It's a bit of a misnomer, but it's one that is kind of accepted, and people know about this. One thing you can do is you can recenter these epsilon ij, so you can define them as demeaned versions of a type 1 extreme value. It will not really change the derivation here. It will increase the mean of the u bar by Euler's constant, and then it's actually really the mean utility, but we normally don't write u bar like that. Good, so it will be soaked up in some constant term that is part of the x, but then again you have a location normalization. That's not important for now. What is important is that the object we want to study here is a random variable, and that is the maximal utility. Okay, so this thing here is the random variable. So I have J, capital J, random variables, and I'm defining a new one, and that is the max of these capital J random variables. Each of the capital J random variables is type 1 extreme value with basically plus a mean utility. Okay, and I'm interested in the distribution of the max of them. I'm not interested in the distribution of every single variable. I'm interested in the distribution of the max of the random utilities. So therefore, I'm writing down something that in the end of the day is a CDF, right? It's the probability that this random variable is less than or equal than u. And we will see in the end why it's useful to write it down like this. But let's just first go through this step by step. This probability that the max utility is less than or equal than u, and u is a constant, is the probability that each of the utilities is less than or equal than u. So that's a joint event. Now, what I'm going to assume, or what I'm assuming, is that these epsilon ij's, these random components of utility, are type 1 extreme value and IID. I haven't made this explicit on this slide, but this is always assumed. So the epsilon ij's are IID. That means independence across J. Since there's independence across J, this joint event here involving J random variables can be written as the product. So the probability for this joint event can be written as the product of the probabilities for the marginals, right? That each of the uij random variables is less than or equal than u. So that's this equality here. And next what I can do is I can plug in the functional form. So uij bar plus epsilon ij is equal to uij. So I'm putting this in, and I'm putting epsilon ij already on the left-hand side of the inequality. So I'm getting that is the product over j of the probability that epsilon ij is less than or equal than u, which is this constant here, this u, minus the mean utility. Good. Next thing I'm doing is I'm plugging in the functional form for the CDF of epsilon ij, because I know that epsilon ij is type 1 extreme value, so I can put that in. Okay, so we have seen that before when we discussed the binary logit model. So that CDF is exponential function evaluated at minus exponential function evaluated at, and now the argument. The argument is this argument here, minus u. So minus this, minus u plus u bar. Minus u plus u bar. Good. And now what follows is simply tricks related to the exponential function. Let me briefly review for you first, before we get into the details, the rules of exponentiation. I'm just going to do this here with pen and paper, pencil and paper. Just to be very clear, exponential function evaluated at a is simply e to the power a. Exponential function evaluated at a plus b is then e to the power a plus b, and as you may recall from secondary school, let's say, this is e to the power a times e to the power b. And finally, what we're going to need is that exponential function evaluated at log of a is equal to a. So they cancel each other out. That's really all we're going to need here. And equipped with this, what we can do is we can say, okay, we now have plugged in the functional form for this CDF, and I'm still having that product operator here. So I'm taking the product over j. Since this is the exponential function that I'm taking the product over, I can use one of these rules of exponentiation, and I can write this as exponential function evaluated at the sum of stuff. So it's simply the sum of these arguments that I'm going to have. So here you see x minus u plus u bar, x minus u plus u bar, and I'm simply getting the sum, and the minus sign is this minus sign here. Next thing I can do is I can say, okay, exponential function of a sum is the product of two exponential functions. This is what I'm doing here. Next step. Then the next step is to see, okay, I'm here taking here the sum over j, but exponential function evaluated at minus u doesn't have a j in it, right? So I can pull that out in front of that sum. So I'm getting this expression here. And then the next thing I can do is I can write this sum here as simply exponential function of the log of that sum. So that's in some sense a bit tautological, but it's going to be helpful. So I'm getting this expression here. And the last thing I can then do is I can take this one here, going from here to here back, to write this again as exponential function evaluated at minus exponential function. And then here is the product of two exponential functions. So it's going to end up being again the sum of the two arguments in the as the argument of this exponential function. So that's the expression we're going to end up with. Now, you might not see it immediately, but what we've just shown is the following. We have shown that the random variable that is defined as the max random utility has exactly this CDF. So here the first bullet point shows exactly the last expression from the previous slide. And what that means is that the max utility is actually itself a type 1 extreme value random variable. with mean equal to Euler's constant plus this expression here. And this expression here is often denoted by I. And that's the log sum term. So it's the log of the sum of the exponential function evaluated at the average utilities. This quantity here is showing up in the denominator of the multinomial logit model. And I is called sometimes the inclusive value, and it is the expected maximal utility. And this brings us back to actually welfare analysis, right? So when I can take a choice set consisting of these J alternatives, and I know the average utilities or mean utilities associated with them, then I can now calculate using this formula the expected maximal utility associated with a particular choice set consisting of alternatives with particular characteristics, and I can play around with that. So if I is the initial inclusive value and I prime is the changed one, for instance, because I introduce alternatives or because I change characteristics of alternatives or I remove alternatives, then the difference here, I prime minus I, is the change in the expected maximal utility. And then what I can do is I can actually translate this into units of money. How can I do that? Well, if I estimate the marginal utility of money, for instance, by having the price as one of the characteristics of the alternatives, so then it would be the coefficient on the price. So if this is alpha, then I can just divide by alpha in order to transfer units of utility, utils. And this is the difference in utils. I'm translating this into, in the end of the day, the expected compensating variation, because I'm looking here at the change in expected maximal utility. And that's just fantastic as far as I'm concerned. So what I can do is I can really find out how much it is worth to somebody that the choice set has changed. Now, the model is great, but it also has limitations. And this quote here is from a paper by Dan McFadden, predating the one I cited in the very beginning, so 1973. And what he says here is that the primary limitation of the model is what is called the independence of irrelevant alternatives axiom. And that axiom he deems implausible for alternative sets containing choices that are close substitutes. So this is very abstract. So for that reason, he provides an example that has become famous. And I just want to give you here the original wording to make that clear. So suppose a population faces the alternatives of travel by auto, so that's car, and by bus, and 2/3 choose to use auto. Suppose now that a second brand of bus travel is introduced that is in all essential respects the same as the first. Intuitively, 2/3 of the population will still choose auto, and the remainder will split between the bus alternatives. However, if the selection probabilities satisfy axiom 1, which is independence of irrelevant alternatives, only half the population will use auto when the second bus is introduced. The reason this is counterintuitive is that we expect individuals to lump the two bus alternatives together in making the auto bus choice. This example suggests that application of the model should be limited to situations where the alternatives can plausibly be assumed to be distinct and weighted independently in the eyes of each decision maker. So what he's saying here is that something can go wrong with this model. Okay, so he's saying that this model imposes some structure that may be fine sometimes and may be very useful and powerful, as we have just seen. But he's saying at the same time that sometimes this structure might be a bad description of the way people make choices. And before we look into how this can be fixed, I want to look at the Hausman-McFadden test. So the Hausman-McFadden test was developed to find out whether the model is a good description of reality, and it's actually also insightful to just think it through in order to understand what this property of the model is that actually might be problematic. Okay, so it turns out that the multinomial logit model, as we have seen it, has a necessary and sufficient characterization given by the independence of irrelevant alternatives property. Okay, so this is the property that McFadden alluded to on the previous slide in this quote. So let us now first understand what this property really means. So the property means that the ratio of probabilities of choosing any two alternatives is independent of the attributes or the availability of a third alternative. This is still very abstract, right? Let us look at this in terms of an example. And the example I actually want to look at is this auto bus example that McFadden already had in his quote. So I find it useful to represent it in the following way. So he said, let's say that 2/3 of the people are going by car. Okay, so this is car and this is bus. Okay, so this is 2/3 of the people. This is 1/3. Okay, so they choose either to go by car or by bus. And now comes a new alternative around, right? So let me just draw this again to juxtapose the two things that he talks about then. So bus 1/3 and car 1/3. Okay. What we would normally intuitively think is that if there's a second bus alternative that comes around, then what will happen is that it will not affect this car choice, but it will just split the probability mass here, the 1/3, into two parts. Okay, so then here I'm getting 1/6, and here I'm getting 1/6 for the second bus. Okay, so this is what people would intuitively think should happen, or many people do think that. What is happening, however, in the multinomial logit model is that the ratio of the choice probabilities for car versus bus, which is 2:1, right? 2/3 divided by 1/3 will stay the same. Okay, so this is exactly what is happening in the multinomial logit model. I'm going to show you also in a sec or in a minute why this happens in terms of formulas. So what that means is that this ratio has to stay the same. So it does mean that when I'm introducing a new bus, it will take away from car and from bus proportional to the initial choice probabilities. Okay, so only then it can actually happen that the ratio of these two choice probabilities will stay the same. Okay, so this is then for the new bus, and intuitively we would think that this should be the choice probability for the new bus. So you can already see here that the ratio of the two probabilities will actually change, right? So here have 2/3, 2/3 divided by 1/6, right? So it goes from 2/3 divided by 1/3 to 2/3 divided by 1/6, and this is a violation of IIA, and IIA means that this stays. Okay, so this stays the same, and this can be symbolized, can be visualized in this way here, that it will take away in this particular way. Okay, so how can we see that this holds in terms of the formulas for the choice probabilities? Well, just remember that Pij was exp u bar ij divided by, here I'm summing over j prime, exp u bar I j prime. So when I'm taking the ratio of two choice probabilities, the denominator will be the exact same denominator for both choice probabilities. So the ratio between Pi1 and Pi2 will not involve the denominator actually. It will simply be exp u bar I1 divided by exp u bar I2. Okay, and this is exactly the IIA property that McFadden talked about. Now let's get back to this test. So the second bullet point is exactly what I just talked about, that the IIA property means that the ratio of the probabilities of choosing any two alternatives is independent of the attributes or the availability of a third alternative, because the third alternative would end up in the denominator of this choice probability, but I'm taking the ratio between two choice probabilities, so the two denominators will actually cancel out, because the denominator is the same for each of the choice probabilities. And we're going to look at generalizations of the model next, but for now this is what we're dealing with. This is the property that is deemed problematic. As a little aside, you can say that this is a bug, but it's also a feature of the model, right? Only because of this property we can actually predict what demand would be for alternatives that have not been there. Okay, so we get the mileage out of this property. So if we can convince ourselves that this property is not so bad, then for the particular application that we're using the model for, then it's very good to actually it gives us a lot of we get a lot of mileage out of it, right? So there's a great advantage to being convinced that this is a good property in the context of a particular application. Good. What the IIA property means, and this brings us back to the test. So if we can't reject the null that IIA holds, then we can make use of it. So how does the test work? The test works like this. It says, okay, when IIA holds, then mean utilities, when mean utilities are of this form, so are linear in characteristics and parameters, then what we can do is we can estimate all but the constant terms from a subset of choices. So first of all, what are the constant terms? So these would be alternative indicators in the xij's. So if and this would go back to a general preference for Coca-Cola, for instance, right? So then the Coca-Cola intercept would be bigger. You have to normalize one of those to 0, like you would have to do it in a linear regression model. But these constant terms are not going to be estimated correctly when I use a subset of choices, but I can estimate all the slope coefficients, say the price coefficient, right? So if all the alternatives have a price and a variation in the price across alternatives, then I can take a subset of choices or a subset of alternatives and I can re-estimate the model. Okay, so the test then does the following. It takes all the data you have, let's say, estimates the model, and then you get the slope parameters, slope coefficients, estimates of the slope coefficients. Say a price coefficient, call this alpha, right? And then you take a subset of the alternatives, and then you only take data where people chose one of the alternatives in the subset, and you re-estimate the model, okay, with this subset of the data. And you again obtain a price coefficient, so that's a slope coefficient, not a constant term, another alpha hat, let's say, and then the test compares these two to one another. Okay, so and if IIA does not hold, then the test will reject, because you will get different estimates of alpha when you choose different subsets. So this corresponds again to this example that you're basically estimating the model when the second bus is not available, and then you're estimating the model again when the second bus becomes available. If the model is not right, in the sense that the model has not generated the data, then you will get different estimates of slope coefficients, and then when you have enough data, you can reject the null that they're the same, and then you have evidence that IIA does not hold. If you have a lot of data and a lot of power for your test, and you cannot reject the null that IIA holds, then you have some evidence in favor of or you have some supporting evidence for the multinomial logit model, and you can make use of its structure to do interesting things like welfare comparisons, and in particular studying the introduction of new alternatives. Good. So this actually ends my discussion of multinomial choice models, at least the introduction to this. So in the next video, what I'm going to talk about are generalizations of the multinomial logit model or other multinomial choice models that do not have the IIA property. Thanks for watching, and all the best.